Hello, everyone. I'm going to present one low light deep learning model for industrial fault detection based on the ultrasonic signal processing. This is Amirhossein Moshrefi. I'm from the École Technologie Supérieure, University of Quebec. First of all, if you're going to check the motivation and the growth of the market, it's around $6 billion by 2028 for the ultrasonic sensing markets and the MEMS. So that's worth to investigate and research on this area. The issue that for the fault detections is that normally the method that used for the detection is like a audible noise in the market, in the industrial, and some conventional methods that are very late to detect. Ultrasonic is the one is the earliest and fastest way to detect. So we're gonna focus on this method, and the detection based on ultrasonic normally it's divided for the pipelines, motors, and electrical instruments like transformers, contact or contactless. We're going to focus on the contact parts, motor and pipe. So far, most of the research that people did on the ultrasonic fault detection are based on the FFT methods, conventional methods, and non-smart methods, and mostly the recent one based on the SVM and some simple classifiers. You can see that normally they're going to detect the specific frequency bands and calculate the energy and consider that it's going to be more than threshold for the faults or not. So the problem is that distinguish between the different type of the faults is hard. It's complicated to detect in the noise environment, and also the model normally is conventional models are handcrafted. Is not that much smart to find the patterns, and mostly they need a lot of parameters. It's going to be more than 1 million, 2 million to detect the faults. And the objective of these projects is to find the high performance, reaching the accuracy around 1, and the accuracy of 100%, and area under curve of 1. And also it should be light in the order of the kilobyte to have a possibility to embedding and for the edge MCU deploying. This is the overview of the flow that I implement. It's based on the microphone array, data processing, filtration, and after the sinc-NET model, BiLSTM and LSTM, and finally to dense. The reason of using the sinc-NET is that if you're going to compare between the normal convolution, normal convolution is based on the kernel size, input and output channels. It's a very huge parameters normally for detection, and but the sinc-NET is very light model. It just have very low parameters. It depends to the output channels, and by practically it's imagine if the normal convolution gonna take 1 million or 2 million parameters, it's around 100 times less, order of kilobyte, and it's very easy to implement on the MCU. The BiLSTM is gonna get past and present temporal context of the flow, and finally one temporal context intensification by LSTM. So this is a final model that based on this flow, it's going to give around 32 kilobytes and have a very high accuracy. These are the 10 different industrial faults that it's very hard to distinguish, and these are the metrics that I used, accuracy and loss. You can see that the validation data is going to follow very accurately the train data, and it's going to give around 96 accuracy. And area under curve of 1, it's based on the true positive rates per false positive. And also it's a very lightweight. Previously, there are some models that I deploy on these boards. This is a board type and that I designed for this application. Normally, we're going to train the model and convert to the C code after using the TinyML library and deploying on the MCU and make an inference for the prediction. This board has a microphone. It's a range of 10 to 80 kilohertz. Is a normal range for the industrial fault detection. MCU and the charging system, detector, and the battery. So the future works is going to be implementing this light model. The previous research I published, it's going to give a higher frequency, high accuracy, but has a memory overloads. So this one going to be there. Good improvement. So the MCU improvement, IoT feature increasing, the optimization for the power consumption, enhancing the memory, and optimizing the PCB going to be the next step of this work. And thank you for your attention.
Thank you very much. Any question?
You mentioned what's the bandwidth of the microphone you're using?
It's around 10 to 80 kilohertz.
80. Oh, yeah, okay.
Yeah.
Any other question? You were referring to the power consumption improvement. Can you talk a little bit about that? How much is, because this is not a handheld device you're developing, correct?
Sorry?
You were referring about the improvement, future work, and the power consumption.
Normally, the power consumption of this device is going to be around 100 to 150 milliwatt. So maybe that's not a optimized version that we have because the huge battery and some extra sensor that I use in this board. So optimization is very helpful because in the industry having the ultra low power is very important. So for the optimization and maybe the decreasing the detection. Maybe currently I'm using the Bluetooth, so maybe ultra wideband is going to help for the better transmission. And the MCU also, it can be changed to the STM. There's a low power STM models. And the LCD also takes a lot of power. That's a first prototype. And this is a novel, detection based on AI for the industrial fault detection. So, and I think it's the first deployment on the AI for this application.